Let's see a simple demo of the segmentation and 3D visualization process carried out on the IVUS images. This is a single patient IVUS video courtesy Piedmont Heart Institute, Atlanta. The IVUS video consists of several images of the inner arterial wall taken at regular intervals using an ultrasound equipment with a catheter which is inserted into the arteries. The catheter is then pulled out slowly and images of the inner arterial wall are taken at every diastole to generate an intravascular ultrasound video. The images from the video need to be extracted and segmented for further analysis. Segmentation of these IVUS images is essential for an effective study of the plaque deposits in the inner arterial walls. To carry out segmentation on these IVUS images, it is necessary to first convert the patient video into a series of IVUS images corresponding to the frames in the IVUS video. What you see on the screen is one such frame or image extracted from the IVUS video that we saw earlier. The first step in the segmentation process is the detection of the outer vessel boundary. A Gaussian filter with a very small sigma value is applied on the original image to blur out insignificant edges. This generates a smoothed image with a lot lesser noise than what is present in the original image. A gradient operator is then applied on the smoothed image to obtain an edge map image. The edge map image thus generated shows only significant edges from the original image. The gradient information from this edge map image is then progressively diffused into the homogeneous regions of the edge map, thus creating a gradient vector flow or a GVF field. You can see the GVF field at 100 iterations, 500 iterations, 1000 and so on up to 10,000 diffusion iterations. The gradient information is progressively diffused towards the center of the image to form a capture range. Once we have a considerably large capture range for the active contour to work on, we initialize a simple snake contour in the center of the image and start deforming it. Due to the basic behavior of snake contours, the contour starts moving towards the desired edges in the image. You can see the progressive deformation and position of the contour at various iterations of the deformation process. We then obtain the final contour after a series of iterations. The iterations are terminated when the contour no longer changes in form. You can see the final outer vessel contour superimposed on the original image. The next step in the IVUS segmentation process is the detection of the inner lumen boundary. Let's get back to the original image here. An adaptive k-means clustering technique is applied on the original image to detect the various regions in the IVUS image. This is the output of the k-means clustering algorithm. You can see different regions in the image represented using different colors. The innermost region represents the lumen area. Edge detection on the clustered image generates a series of boundaries or edges. The innermost boundary is essentially the lumen boundary, which is what needs to be extracted. So we start the GVF process again by initializing an initial contour and deforming it to obtain the final inner boundary. Here you see the final lumen contour superimposed upon the original image. So now we have an outer vessel boundary and an inner lumen boundary, and you can see a high percentage of accuracy in the edge detection. Once we have these sets of outer and inner contours, we move on to the 3D reconstruction process. Previously obtained sets of contours are stacked on top of each other to obtain a tubular structure. However, since the IVUS images or frames were generated at regular intervals, we need to create intermediate sets of contours to give a sense of reality to the stacked volume. The interpolation process is just an approximation and may not fully reflect the original artery at that position. Once the tubular structure is created as a 3D volume, appropriate software can be used to view this volumetric data. What you see on the screen are different 3D views of the same surface volume. You can see both the outer and inner boundaries, seemingly as outer and inner surfaces of the arterial wall. A transverse section of this tubular structure shows you the outer vessel boundary and the inner lumen boundary. The intermediate area is filled using a region filling algorithm. This area represents the plaque deposits in the coronary artery. This information can further be used for calculating the volume of the plaque deposits. This is potentially important information for further analysis like calcium scoring and diagnosis of coronary artery diseases. Thank you for watching.